I'm absolutely delighted to see this room so full that people are having to search for seats, even though there's some seats at the front here. Please do come and join us. Let me make a couple of housekeeping announcements first. There is a list there of people whom the Institute think are coming to the big fancy dinner on Wednesday. Please check that you're on there if you think you should be on there, and you're not on there if you think you shouldn't be on there. And if you need to make a change, please go and see the Institute staff at the desk. Then the second thing I need to say is, because of the way the recording's done in this room, the Institute do ask us to have all mobile phones turned off while you're in this room, please. And also, no use of laptops during the lectures. So if you could turn off your laptops and your mobile phones, please. So now to the more formal bit. I'm going to tell you a little bit of the history of this conference. About 4 years ago, my colleagues Steve Gilmore and Basha Bagatska and I were applying for a grant from EPSRC. And we thought it would be nice to, at some point during the grant, actually have a one-week conference on design of experiments where people from different parts of design would talk to each other. So we got the grant, and a year later, Heiko Grossman joined us, and we raised our sights a bit. We thought rather than a week, we would apply for a 4-week program here at the Newton Institute. First 3 weeks being sort of heavy interaction, and the final week being this conference. But by then we'd expanded again in terms of subjects, and we thought we wouldn't just have design people, we would also focus on 3 particular application areas: clinical trials, computer experiments, and all the omics, genomics, proteomics, etc. And you will find there are 3 theme days in this conference dedicated just to that. Well, by the time we'd got the permission for the go-ahead for this, there had been the very successful 2006 DEMA conference at Southampton, and Dave Woods had shown how good he was at organising things, so we brought him on board too, and he's been the one who's been chiefly responsible, with help from the rest of us and others, for organising this week. So I want to say a big thanks to Dave for being in charge of this week, everyone who's helped us along the way. I want to thank our sponsors who've helped us financially, and that has enabled us to get some more young people here. I want to thank the Newton Institute staff, because they are absolutely marvellous. We've just had to see to the scientific side, they've seen to everything else. Dave, have I forgotten anybody?
I think Heiko as well needs to mention.
I did mention, yeah, but yes, I have to say. All right. I forgot to say that Heiko and Dave together, but you were doing this week. So I think it now remains for me to hand over to David Cox. We're delighted to have him here to give the opening talk of the conference. He is famous for giving talks with a single word title. I remember several years ago hearing a talk with the simple title, Interaction. Here he is now, just randomisation. So I look forward to hearing this. David, if you'd like to come up, I'll just switch off the other housekeeping notices and leave it to you.
Oh, thank you very much, Rosemary. Thank you for the invitation. It's a great pleasure to be here. Our subject of the design of experiments no doubt has a long history, but for our purposes it's probably enough to start with Fisher's, now see if this thing works, with Fisher's paper, and then leading not too long afterwards to his famous book. But we should note also another great masterpiece of the subject, not so well known, Yates's Technical Communication 37 on the design and analysis of factorial experiments. 1937, I think, represents not a plateau in the subject, but the end of a period of extremely rapid development. The Rothamsted people somewhat switched their attention to survey work after that. A few years later, I think at Yates's suggestion, David Finney developed fractional replication. The next main development in the subject was probably in the 1950s, with the emphasis experiments with factors with quantitative levels, but not so much that as with the notion of looking at the response surface and its properties rather than at the effects of the individual factors. Clinical trials, I've unaccountably missed out as issues of current development, computer experiments, but I was thinking perhaps also from a more immediately applied end, in addition, issues of the use of randomized trials in investigations of social policy, matters that the so-called Campbell collaboration is trying to pursue by analogy with the very successful Cochrane collaboration in randomized trials. And it may be that computer experiments and issues of social policy will be areas where new technical developments in the design of experiments will be motivated. And then, of course, one has to remember, connected with all this, the more formal mathematical theory of optimization. Now, Fisher had, excuse me, Fisher had four principles, basically. Factorial experiments, blocking Latin squares and so forth for the local control of error, replication, and finally randomization. And of those, I suppose randomization, it's not necessarily the most important. It might be argued it's the least important. But randomization is certainly the most enigmatic of these and the one that's caused the most general discussion. Now, there are three, I think, quite different lines of attack when one thinks about the justification of randomization. The first, and in many contexts by far the most powerful, is the notion of avoidance of selection biases of one sort or another, biases in measurement. Whenever the human senses are involved in choice or measurement, there's the possibility of bias. And randomization is often a very effective way of controlling for that, and sometimes it's almost obligatory. Sometimes one could go as far to say that if an experiment is not randomized, it's seriously defective. And that, I think, is relatively uncontroversial. Even students who didn't agree with the use of randomization in agricultural field trials argued quite persuasively in his final paper against randomization in the field trials, was absolutely convinced about the necessity of randomization for the avoidance of various kinds of personal bias. There's the possibility of using randomization to form the basis for a secure estimate of error in standard analysis of variance or least squares analyses of traditional experimental designs and perhaps not so traditional experimental designs. And then there's the becoming more technically statistically, there's the possibility of basing exact tests on randomization. I'm going to concentrate largely on the second, but say something first about the third, about the randomization significance test. But first, just a word about Bayesian and decision-based approaches to randomization. Some of the early workers on the personalistic Bayesian approach to statistics argued against randomization. L.J. Savage certainly did to begin with, but I think he somewhat retracted when it was a question of selection biases. I quite vividly recall a debate at the British region of the Biometric Society in which Dennis Lindley argued I was the sort of other speaker. Dennis Lindley argued very persuasively against any use of randomization as counter to the personalistic Bayesian ideas, and I'm sure he won the debate, even if I think he was totally wrong in just a little personal prejudice. But there is an issue here, of course, of what the purpose of a design is, and also that design choice is a decision problem. If there's a distinction between inference and decision making, it would be that in inference you might say, well, there's this explanation and there's that explanation. They both fit the data reasonably well, and our data, we remain undecided. In a design problem, you might say, well, there's this design, and they both seem reasonably applicable. Well, we've got to choose one of them. So it's a decision problem. And therefore, issues of using all the possible information one can and of considering the consequences of doing the wrong thing do arise. And Fisher, in a sense, resolved that issue very elegantly, because the Fisherian principles say, basically, use all the background knowledge that you possibly can, for instance, in forming blocks or using Latin squares or whatever, in designing the experiment. But then, by randomization, have an analysis, an interpretation that does not depend on those assumptions that you've made. The efficiency may so depend, but the actual validity of the interpretation doesn't. So he, in a sense, very cunningly resolved the issue of using all sorts of possibly vaguely specified knowledge in choosing a design, but having a self-contained analysis that didn't depend upon those assumptions. And I think the point, of course, is that for most purposes, experiments are not done solely for the edification of a single investigator, in which case one might argue that personalistic Bayesian arguments would become more relevant. But they are, to some extent, or possibly even to a very, very great extent, for public consumption and to be convincing to people who perhaps have different prior views from the investigator. Well, that's all I'm going to say about that particular issue. Something about exact tests. The standard assumption that one would start from is perhaps can be traced back to Neyman, that if we apply treatment, apply a particular treatment to a particular experimental unit, the outcome is a sum of a treatment and a constant characteristic of a treatment and a constant characteristic of the experimental unit, whatever the allocation of treatments to the other units might be. And a null hypothesis would be that all these tors are the same and that so the treatment's totally ineffective. Now the point of that assumption is that to begin with at least, those A's are not random variables, they are just arbitrary unknown constants attached to the experimental units, whatever it might be. Now the history of using that as a basis for significance tests, I think is roughly this, that at some point Egon Pearson, in reviewing Fisher's statistical methods for research workers, raised the question, were his procedures unduly sensitive to normality assumptions? And robustness was not a word used by Pearson, but he was really the first person to investigate robustness issues at all thoroughly. And Fisher's reply to this was to set up a randomization analysis in which he based a test of the equality of means, and implicitly also of confidence interval, fiducial intervals. He based a test of the equality of means solely on the randomization, on the fact that the A's that go with a particular treatment are chosen at random in some defined way. And he showed with one example pretty close equivalence between the normal theory results that he obtained and randomization tests. And Student at some point, Student was of course very, in a certain sense, very close to Fisher, but disagreed with him on various things. Fisher, in his final posthumous paper, Student remarked rather tartly about Fisher's extreme ability at reaching great generalizations from a single set of data. So it was a bit, Fisher's conclusion was maybe a bit sweeping. In the later 1930s, workers at University College London, Welsh, Pittman and others developed the idea of the randomization test essentially by calculating the permutation moments of certain statistics and appealing to a very basic principle of Karl Pearson's, very basic and important principle, which says that all distributions are virtually exactly determined by their first four moments, which that's meant to be a slightly joke, but no, well, that is essentially what Pearson was saying. And of course the interesting thing is that that principle used with a bit of judgment and so forth is remarkably effective in many contexts. There's a relation which will come up again later with the infinite model theory, in that if one thinks of the randomization being if one thinks of the A's as in fact being random variables and generating a permutation distribution from every set of A's, then if you put all those distributions together, you must get the infinite model theory. So certainly in large samples, there can't be too big a discrepancy between the randomization permutation test and the appropriate infinite model discussion. Now, what are the practical implications of this? The most important practical implication is the possibility that the inference that you make is solely self-contained, in the sense that there is no assumption that these A's are random variables or chosen or stochastic in any sense. They can be totally arbitrary. All the one's saying is that from the results of the randomization analysis, we can produce a conclusion about what was really going on in the particular experimental units that we happen to be using, in concluding something about whether or not the application of a particular treatment to a particular unit had an effect or not. But the inference is internal to the experimental units that you happen actually to have used. And I think philosophically that's the most interesting point. Now you might think that this discussion, which was very active in the 1940s, 1950s, some extent 1960s, is an arcane thing of history. But last week I got the latest issue of the Annals of Applied Statistics, the new applied journal that the Institute of Mathematical Statistics has set up. And in there you find a paper by Zeng and Marvin Zelen on randomized trials, arguing precisely that the appropriate framework for the analysis of randomized clinical trials is this analysis here, because Zelen, I assume this is largely Zelen, I don't know. Zeng and Zelen argued that the patients in a randomized clinical trial are in no sense whatever a random sample from a population of patients that one might wish to consider. So that the notion of thinking of these A's, which represent patient effects in that context, the notion of thinking of them as random variables from a meaningful population is inapplicable. But of course that argument can be applied almost universally. I can't recall having been involved with or having seen a randomized trial experiment in which the experimental units were randomly chosen. They're normally very deliberately chosen, either as patients willing to give informed consent to some procedure, or often in other contexts as giving the conditions under which the effect one wishes to study is likely to show up in its most striking form. In a recent investigation of bovine tuberculosis that I had some connection with, for example, we chose the regions for a randomized study to be the ones in which there was most tuberculosis. It would have been ridiculous to have used a random sample of regions in the country where in most of them there would be very little disease to study. We put the experimental units deliberately in the regions of highest incidence. The randomization was in the randomization of the treatments, not in the selection of the units. So Zeng and Zellen's argument is in fact really, I think, an almost universal argument for using in principle at least, the randomization-based analysis. Now, Yates, although Yates didn't take that route, Yates put a lot of emphasis on the randomization for the estimation of error, but then as least squares as the appropriate method of analysis. Not as least squares as an approximation to the randomization analysis, but as least square, but he wasn't, I think, terribly interested in the randomization analysis as such. Kempthorne, who'd worked with Yates before he went to Iowa, and was very Fisherian in his approach to many things, he took the view that the essentially the same as Zeng and Zellen, that basically the randomization procedures were the appropriate ones to use, and that the only reason for not doing at that stage was the computational problem of handling the detailed work that would be involved, and therefore he saw least squares as a convenient approximation to randomization distribution. So there's a general issue, perhaps not an immediately practical issue, but an issue of what it is one thinks one's getting at by doing an experiment. Is one drawing some conclusion about applying to some population of future individuals, or is one actually trying to uncover with security what has been going on in a particular instance? There's the issue that I come back to later, that there's a difficulty with randomization in small studies, and in particular if the randomization set is extremely small, the most extreme level of significance one could ever get would be quite high. The p-value would be quite high, or correspondingly one could not draw confidence limits at more than a certain level of security. But then caution about very small studies is really wise. I think there's also the implication, which is somewhat counter to one of Rosemary's recommendations in her work, in her excellent recent book, which is that in randomizing a Latin square, it's not necessary to randomize the treatments, randomize the rows and the columns, but not the treatments. It would seem that if one's interest is in the relation between the randomization theory, permutation theory, and the infinite model theory, the richer the randomization set, the better. Therefore, one might get better agreement by using as much randomization as one possibly could. Kempthorne had a doctoral student who investigated this, but I'm unable to trace. I don't think it was ever published, and I haven't been able, I'm afraid, to trace the conclusions that he reached, which I think were not the ones that I've just indicated, perhaps showing that Rosemary would be right after all. on that particular point. Well, now I want to turn to second order theory. And here the principle, this is perhaps familiar, but I would like to go over it. We start as before with this idea that there's a treatment effect, a treatment parameter, and a unit parameter, and what we observe is the sum of the two. We randomize, form a linear model, which puts constraints on if there are constraints on the randomization, such as randomized block, Latin square, or whatever, we represent these by parameters in the linear model. We then define estimates essentially by least squares, and we aim to show that these have desirable properties under the randomization distribution. Essentially, that the expected value under randomization of a contrast, I put a simple difference, but of a contrast is what it should be, and that the variance, now the variance of this difference and the expected value of the residual mean square will certainly be quadratic forms in the A's. The tors won't enter. Both those things are quadratic in the A's, and the issue is, are these two things essentially the same? And that depends upon the randomization being appropriate. But if the symmetries are such that the two forms are proportional, then by inheritance they must be equal. Well, I think I'll take the liberty of deferring exactly what I mean by inheritance in a moment, but broadly it's the possibility of passing from a sample to a finite population to an infinite population. And there are clear group theory implications of this, which were, I think, first pointed out explicitly by Grundy and Healy in 1951, and Rosemary's developed these extensively. Uden developed somewhat similar ideas independently, because they have the implication of sometimes being able to exploit this idea of restricted randomization, in which certain patterns in the randomization are labeled as bad news, but one can say, for example, that certain Latin squares are undesirable. That one should have a randomization set that has the right properties to ensure behavior of these cues, but which excludes the unpleasant arrangements. And Uden had this idea independently. And just to go very quickly over the argument, if we think of a randomized block design, we can say that the starting assumption is that we've got an A that depends upon the block and the plot within a block, and a treatment. Let's look at the expected value of the randomization of the residual mean square. It's clear it doesn't depend upon the tors. It's quadratic, and it's such that any two A's in the same block, any product like this, J in block C and K in block C, all those things are the same, and any two A's in different blocks are the same. Equivalently, we can write it like that. Then the argument is that this is an identity which holds for any A's. So if we put all the A's equal, these two things vanish, the residual mean square vanishes, therefore this term vanishes, similarly that term vanishes, and we're left with this. Now the question is, what's the expected value of the residual mean square? It's some multiple of the sum of squares of the A's within blocks. This is where inheritance comes in, because now one says, supposing that the A's were in fact, shall we say, IID N01. This is not a statistical assumption, it's a mathematical assumption of saying this is an identity, and therefore it applies even in that case. And we can take expectations over the distribution of the A's, and then because we know the overall expectation of this will then be 1 over r minus 1 into t minus 1. That determines the value of c dash. And a similar argument applies there. That's this argument of inheritance which Fisher put forward in a different context of going from a finite a sample to a finite population to an infinite population, that appropriately defined a property from can go from one to another to the next stage. Now, why is this important? Well, first of all, because it gives a unified model for all standard designs. It means that if you have a split plot experiment with the split plots in Latin squares and the whole plots in randomized blocks, the assumption that's involved for analyzing that is no different from that of any other design. And the linear model that's conventionally used to analyze such things is in fact a consequence of the randomization. Otherwise, the analysis of all these special designs, the classical designs in the literature, it looks as though, and the way this is often presented in textbooks, it looks as though a special model has to be dreamt of for each new situation. And that's not right from this point of view. All the models are a consequence of the randomization and a single unifying assumption. The argument doesn't apply directly to analysis of covariance or to crossover designs. Now, I just say a word about Neumann's generalized model. Oh, I'm going the wrong way with it, these things. The starting assumption is that is of unit treatment additivity. Now, Neumann, in a celebrated paper in the mid-1930s, read to the RSS, argued that one should generalize that model and allow for treatment by block, treatment by row, treatment by column, treatment by unit interactions. That one should not assume that every the effect of a particular treatment is identical in every plot, let alone that it's identical in every block. And he developed this, and this led to the suggestion that in fact Latin squares were biased in a certain sense. And this provoked the intense fury of Fisher. It's worth reading the account of the meeting, which is a blow-by-blow account. Of course, it's well before my time, but people who were there spoke with awe of the occasion afterwards. It makes any Royal Statistical Society meeting of the last 50 years pale into utter insignificance. It really was a very furious argument. Now, what was behind it? And I don't, well, this argument in a way drifted on. Kempthorne and his associates, Wilk and Ziskind, in papers in the Annals of Statistics, Annals of Mathematical Statistics, in the 50s and 60s, 50s anyway, followed this up. And indeed, Kempthorne at one point said the Latin square should not be used because it was biased. Now, what was going on? Well, it was a mistake, I think, a conceptual mistake of Neumann's and Kempthorne's, that which is another thing that keeps recurring. What they'd done was to say, okay, two treatments, the difference between two treatments can be different in different rows, different of a Latin square, or different blocks of a randomized block design, but averaged over the whole field of the experiment, the difference was exactly zero in a null hypothesis. So they were implicitly setting up a hypothesis in which interactions were present but main effects absolutely absent. And it's pretty well established that in general, with very rare exceptions, that is not a sensible hypothesis to consider. And in fact, I think the issue was resolved. There were two short papers in 1958, one by C.R. Rao, one by me, that I think virtually explained why that was a bad idea. That was just an instance of a very plausible sounding generalization. It's very natural to say, that's a terribly strong hypothesis. It's saying, and to some extent untestable, that if the difference between two treatments is exactly the same throughout a field or throughout whatever the experimental units are. It's very natural to say, well, let's be a bit more general than that. But the moral is that having done that, you have to be very careful about what questions you ask. Well, for analysis of covariance, we argue like this. I talk about, it could be done more generally, but we find the regression. Suppose now we have some concomitant variable Z, and we find the adjusted estimate between two treatments, difference of their means, regression coefficient of Y on Z, dot residual means adjusting for blocks, rows, columns, what have you, and then the difference of the Z's. And so beta is a column vector, I guess. No, it can't be, can it? It must be a row vector, and this is a column vector. You put all that together, the variance is this form. This is the sum of squares and products of the Z's. Under randomization of the design, we can study the behavior of the concomitant variables, and they all have this simple property here. Now, the reason that we can't immediately apply random permutation theory or randomization theory to analysis of covariance is, of course, as a denominator to this, an inverse matrix in general. And the theory that I sketched at the beginning depended essentially on dealing with linear and quadratic functions of the data, whereas now we're dealing with more complicated things. So we have to rely on asymptotic theory, and in particular on the possibility that these things are small and that this suitably normalized is converging in probability to something. In other words, imagine a whole series of bigger and bigger and bigger experiments in the way that one in imagination does in asymptotic theory. And when you do that, you come up with the fact that the variance over the randomization is 2 sigma squared over R is the number of replicates per treatment into 1 plus WP over the residual degrees of freedom. Now, the WP is basically this thing here, and if that were constant, this would be a squared distance and would be having a chi-squared distribution under in the light of the fact that the Z's have the same mean. So we get that result, where WP has approximately a chi-squared distribution. The approximation is the approximation of treating the inverse covariance, inverse matrix of sums of squares and products of normalized as having converged to its limit in probability. Now I put as a naive interpretation of that. The naive interpretation is, because we haven't designed the experiment yet, we haven't measured the concomitant variables, we're proposing to include them, then we should take expectations over WP, that's P, so this becomes 1 plus P over residual degrees of freedom, and basically that means something like, because the residual degrees of freedom will be roughly the total sample size, that means losing an observation for each concomitant variable included. And in many contexts you might say, well, that's going to be, certainly a clinical trial context with hundreds of patients, that's negligible. The not quite so naive interpretation is to say, well, Yeah, but that's only averaged over all possible designs. We might be a bit unlucky and get a design in which WP, which has a chi-square distribution, is somewhat towards the upper end of its distribution. So perhaps we should be using, for design purposes, to be slightly on the cautious side, something like perhaps the upper something or other point of the chi-square distribution, which would make the p substantially more than p if p was quite small. That rule of one observation lost per each concomitant variable included does ignore all sorts of complications, but you will find it quoted in the literature, I think. But I think it's a bit on the possibly under cautious side. But there's a more serious point connected with this. We do the design and we find a particular value of WP. What I talked about a moment ago was at the planning stage. What should we do about including concomitant variables? Should we include them in principle or not? But now suppose we've used the design and got a particular value of WP. Now we know we may have been lucky or unlucky, and now we're in the general inferential issue of how do we make frequentist inference compatible with the need to interpret the data that we actually have. Recall that Fisher quite often, I think, used the expression the unique data under analysis, despite the fact that his justification for his arguments was basically based on a frequency view of probability. He talks about the unique data under analysis. And how does one resolve that issue? Well, it's not done by students in this paper that I mentioned earlier. He was criticizing the notion of accepting. You randomize a design and the result is obviously a very unpleasant design. It's got bad properties. And he talked rather sarcastically, I thought, about people spending a blameless life repeating the same experiment again and again. They would be all right, but that really wasn't the issue. And Fisher, of course, resolved this in his view, a special view of probability. The probability had to be both frequency-based and appropriately conditional, that there should be no recognizable subset. And it seems to me this is, in principle, a very crucial point, not just in the present context, but in general. However difficult it may be to set it out in a form that satisfies the wish to have a very clear-cut mathematical formulation. So the issue then is that analysis, randomization based or not, should be conditional on WP. And it seems to me, therefore, that at the design, that if you had the Zs at the design stage, what you should do is to keep re-randomizing until WP, before you've got the data, of course, you keep re-randomizing until WP is somewhere acceptably small in the lower tail of its distribution, and then rely on the asymptotic joint randomization analysis of all these variables. And I point out that if you do that, if you apply this to imagine that you've got a randomized block situation, but you start to analyze it as if it was completely randomized, and then you say, oh, but I've got blocks, I'll represent blocks by, sorry, you start to design it as if it was completely randomized. Then you say, okay, we represent blocks by a series of indicator variables and adjust for blocks by analysis of covariance. Well, if we follow this procedure that I've outlined and went on re-randomizing until WP was in fact 0, you would recover the correct randomized block analysis. I put in here the need for a well-judged level of abstinence. That's not just a general moral for life, but this. It's sometimes objected to. Richard Royal, particularly in a sampling more than a design context, objected to randomization essentially by saying, well, whatever design you come up with, there's always something peculiar about it, and therefore the randomization based, and this something peculiar can't be ignored, shouldn't be ignored. And therefore, the gain from the randomization is a bit bogus. And the answer to that is, I think that he's in a certain sense absolutely right, but not about it being bogus, but what it really means is that one should look at designs critically to see if there is anything odd, unusual about them that needs a special adjustment. But in a certain sense, one shouldn't look too hard, that there are penalties in looking too hard. So that's what I mean by a well-judged level of abstinence. Well, in a sense, I've already discussed this, but I thought I should say just a word about Student's last paper, published posthumously. He'd submitted it to Biometrica. There'd been some referees' reports, almost certainly from Neyman and Pearson, and these had not been dealt with because he was working on them immediately before he died. So it was published in this. Now what Student was doing was, first of all, he was saying randomization is undoubtedly highly desirable for dealing with issues of selection bias. That was not disputed at all. But when it came to agricultural field trials, he felt that he could always do better than a randomized block or Latin square design, and he set out to show that by analyzing uniformity data. Following his paper, I think either in the same issue of Biometrica or the next one, Yates had a long paper in which he really somewhat criticized the way Student had analyzed his systematic design. But more importantly, I think he made a statement which I paraphrased somewhat here. He agreed every arrangement that one might come up with may be recognized as having some special features, but with skillful design, any differences in precision are likely to be minor. One of the objectives of skillful design should be to randomize within a set such that you're reasonably satisfied with all the designs that might arise. And they said, therefore, it's best to randomize, obtain a secure estimate of error, and concentrate one's attention on interpreting the effects that you've found, rather than, as he felt, going for a systematic design and then having to worry about whether the error had been correctly estimated. Because with a systematic design, there will be a question of how the error is appropriately estimated to take account of the constraints. Well, that was in the late 1930s. The whole issue, in a way, was resurrected not that long ago in connection with neighborhood balance designs, where there was the argument that by using optimal design theory and the general notion of spatial dependence, that plots close together were more likely to be alike than plots further apart, that one could do better than the randomized designs in the agricultural field context. A few miscellaneous points. I've said nothing about what in a way is perhaps the most interesting, or one of the most interesting aspects of this, which is I suppose that the randomization is basically in one step, but of course in clinical trials it's not, very much not, and there's the notion of sequential randomization. Anthony Atkinson's important work on that, There's the bias coin design of Efron. But I think the same principles apply. That if you introduce additional balance into the design over time in the sequential randomization, then in principle at least some account of that has to be taken in analysis. There's a notion of what I've slightly vaguely, well more than slightly vaguely called semi-randomization. There are many practical contexts, I suspect, where in a way the practical issue of experimental design I think is almost always that how do you obey these important general principles that we're all familiar with, how do we adapt those to the constraints of the particular practical application? And there are very few practical applications that don't have severe constraints of one or another. So by semi-randomization, I think I've just time to say a word in a little more detail about this. There's been some controversy recently about the effectiveness of lung transplantation in patients with cystic fibrosis. It's an operation of desperate operation in a sense. British data seems to suggest that it improves survival. A recent study of American data suggests by and large the opposite. And of course this is observational data. Selection biases are probably rampant in the data. The most obvious randomized trial is completely inappropriate. The most obvious, the constraint on the system is the availability of donor organs. The most obvious randomized trial would be to get pairs of patients, when a donor organ becomes available, get pairs of patients who are suitable to receive the organ, choose one at random to be transplanted, condemn the other never to be transplanted, and clearly that's totally unethical and inappropriate. Another possibility would be to choose the pairs of patients that I've described, randomize one to be transplanted, and give the other patient in the pair total priority at the next available opportunity. Now, for that to work as a design, it's important that a reasonable proportion of those patients die before they get to the head of the queue. But leaving that aside, what it essentially means is that something like half the patients are transplanted when they would have been otherwise, a quarter move forward a bit up the queue and a quarter are delayed. Now, I suggested this at a meeting of surgeons and clinicians a few weeks ago. I'm still alive to tell the tale. I wouldn't say they leapt with enthusiasm at the idea, but at least it wasn't totally rejected. And maybe something like it will be the basis for a method of resolving this really very crucially important issue. I mention that just as an example of the kind of constraints that practical conditions can put on what one might, in theory, like to do. Random balance, in effect, I've already dealt with by the notion of dealing with conditioning. Mendelian randomization, I haven't time to discuss. Three roles of randomization: bias removal, error estimation, and exact tests. Arguments against randomization: maybe you can always do better. Maybe there's some more intuitive argument about sacrificing control. I talked a bit about second order theory of randomization and the role in it of conditioning. The unclear role of exact distribution theory. And I'd point out at the end that there is, of course, a parallel, in a way more lively discussion of these issues in sampling theory circles between so-called design-based and model-based discussions of sampling problems. There the issue is more clear-cut, perhaps. I'm talking about the kind of sample survey which is designed to study a specific finite population, not an analytical survey or an observational quasi-experiment, but a study of a specific population. So you have your finite sample, you have your finite population. In the model theory, you imagine your population embedded in an infinite superpopulation. Your inference goes from the sample to the superpopulation and then back to the unobserved members of the sample. Now that's a beautiful and elegant argument, but of course conceptually it is pretty contrived. And the interest in the finite population is much more explicit there. So the interest in this issue of whether one should be using model-based or design-based, randomization-based analyses is probably more, it's similar to the issue in the design of experiments, but perhaps more pertinent. What I said nothing about, but intended to say a little, is the role of randomization in non-normal theory-based analyses. Because after all, nowadays, many of even of the relatively standard designs will be analyzed by log Poisson regression or logistic regression or what have you, not necessarily least squares. So that's a quick survey, largely of history, but with a few new points here and there. Thank you very much.
Thank you very much for that. We actually do have time for one or two questions or comments. Does anybody want to ask a question? Henry?
I've always thought that the emphasis on randomization was rather particular to medical and social sciences, where there's a unwillingness to move outside the population being studied, whereas in the rest of science, what you said, the superpopulation approach is used really to increase the portability of the modeling to outside the immediate population being concerned, and then I find it rather hard with the randomization approach to have the same level of portability. For example, I mean, is a study done in England portable to a similar population of Holland without some superpopulation aspect to the modeling?
Well, the issue is it exportable at all, isn't it? I mean, that's concerned the interpret. I mean, the really key point about randomization is the avoidance of selection bias, and that's, I think, not what you're talking about. It's this issue, isn't it, of what is the population to which your conclusions apply. And there's a paradox here, isn't there, between, and I tend to, I think, agree with you. There's a paradox here between the notion of the totally secure experiment, which is, and for that matter, the total secure sample survey, which purports to give conclusions that are totally internally based and not involving strong assumptions about anything, with the fact that in any scientific application, one's concerned with putting together pieces of information, often of different kinds, and so that the security of each individual investigation may not be quite so crucial. But if you want to extend the conclusions from a British study to a Dutch study, or even more, well, went further afield, it seems to be crucial to see, first of all, in what important respects the Dutch population might differ from the British population, and whether the treatment effect that you're investigating interacts with that difference. In other words, is it stable with respect to that feature? Because if it's not, the generalization you get out of the infinite model is an illusion.
I can see that there are some other people who would like to ask questions, but I'm aware that it's almost 11 o'clock, and that's time, isn't it, for the poster storm. Given how tightly we have to do the timing on the poster storm, I'm going to thank David now, and you will be around for doing coffee for people who ask you questions, I thought so. Thank you again for that.